Hey, Elysia.
Hi.
Hello. How was your drive back home?
It was good.
That was
I
good.
had to drive to Martinez from Richmond, so I
Uh-huh.
drove a little fast.
Oh, what was the max speed? Like, oh my God, that's scary.
90.
90. Oh my God. 90. Oh my gosh. Oh my God. Um, when you told me you were driving home, I was like, I thought you said you gotta drive home in the morning.
Oh, well, I did this morning. I drove
Uh-huh.
back home.
You're back
And
home.
yeah, but I'm here. I'm going to my sister's place.
Right, right. I see. That's good. Yeah. Caitlin is still in Mexico with her sister. Okay. Yes. So right now I'm just going over oxidation and reduction with Kathy Farha because she hasn't gone over this yet. So this is the new table I just made for oxidation and reduction, which might make sense for you. So best topic, yeah, for 118A Ochem 1. This is like towards the end of it. Um, Oxidation and reduction. There's three ways you could think about it. You could think about it in terms of electrons, in terms of the bonds to electronegative atoms, or in terms of the bonds to hydrogens. So oxidation and reduction, when you think about it in terms of electrons, that's more the Gen Chem way, right? With the oil rig and Leo, the line says Ger. Um, Oxidation is going to be the loss of electrons, whereas reduction is going to be the gain of electrons, right? And there's two ways that you could remember that. You could remember that as oil rig or Leo, the line says Ger. Oil rig is going to be oxidation is the loss of electrons. Reduction is the gain of electrons. That's oil rig. You could also think of it as loss of electrons is oxidation, gain of electrons is reduction, right? But more organic chemistry related is going to be talked about it in terms of bonds to electronegative atoms and hydrogen, right? Where oxidation is going to be the gain of bonds to electronegative atoms. It's part of the name, oxidation. We're adding bonds to oxygen, let's say. And then reduction is going to be the loss of bonds to electronegative atoms. We're reducing bonds to electronegative atoms. But if you think of it in terms of hydrogen, which is the anti of electronegative atoms, oxidation is going to be the loss of bonds to hydrogen, whereas reduction is going to be the gain of hydrogen's bonds, right? Gain of bonds to hydrogen. So now I'm just going to move on to oxidation of alcohols, and I want to describe what an oxidizing agent means. Whenever you see an agent, that is going to be a reagent that does something else to a molecule. So an oxidizing agent will oxidize another molecule. Right. And there are two types of oxidizing agents. There's a weak oxidizing agent and there's a strong oxidizing agent. A weak oxidizing agent is going to be PCC and it's a product solvent CH2Cl2. A strong oxidizing agent is going to be Jones reagent, right? But there are different forms of Jones reagents that you could see. For Wei, you just have to know Jones because she did not go over the other forms of it. But the other forms of it will have a lot of chromium and oxygens. So you could see it as Na2Cr2O7, acid and water. And you could also see it as CrO3H2SO4 and water, right? And there is a commonality between these three agents. There is chromium and a lot of oxygens. A lot of oxygens. Um, are those so this is the weak oxidizing agent that you will see for 118A. 118B, 118C, you'll learn more about oxidizing agents and reducing agents. But when you first get introduced to this idea of oxidation and redox reactions, these are the two that you have to worry about for 118A for now. PCC and Jones. Know which ones are weak, which ones are strong. The weak is PCC, the strong is Jones. Okay, so if I say those two, then it's weak and everything else is strong. Yeah, if you see these two together, it's a weak oxidizing agent, and then everything else is going to be strong. Yeah, you could think of it like that. But it's best if you like associate these reagents with Jones reagent and associate Jones reagent as a strong oxidizing agent, right? Because when you learn about 118B, 118C, these reagents are going to build up onto each other, and you have to like distinguish which ones are weak, which ones are strong, and if it's an oxidizing agent or if it's a reducing agent, right? Yes. Example of strong oxidizing agent is potassium permanganate, which is going to be introduced in 118B. Chlorine gas, hydrogen peroxide, which is going to be in 118B and C. Yeah, but for 118A, it's going to be PCC and Jones. Okay. So now let's talk about the oxidation table that I showed Elysia last time. There's going to be 3 different kinds of alcohols that we're going to work with here. We're going to work with a primary alcohol. We're going to work with a secondary alcohol. And we're going to work with a tertiary alcohol. Right. And let's say we want to oxidize these alcohols using the oxidizing agents, right? When you think of oxidizing agent, that's an agent that would oxidize a molecule. And the molecules we're oxidizing here are these different alcohol types, right? Primary, secondary, and tertiary. Do you know the differences between them, like primary, secondary, tertiary alcohols, and why they're different? Yeah, you don't. Okay. So what it means for a primary alcohol is that once you find the alcohol group, which is the OH group, find the carbon attached to the carbon. If this carbon here is attached to one other carbon, which this one is, then this is a primary alcohol. If this carbon here, which is the carbon directly attached to the alcohol, is attached to 2 other carbons, these 2 carbons here, 1, 2, that's what we call a secondary alcohol. But this carbon here, the one directly attached to the alcohol, this carbon here is attached to 3 other carbons, 1, 2, 3, making that a tertiary alcohol. So that's the differences between a primary, secondary, tertiary alcohol. Okay, so now we're going to oxidize these alcohols using the oxidizing agents. One is PCC with its aprotic solvent, CH2Cl2, and the other one is going to be Jones. Right. This one is going to be a weak oxidizing agent, and this one is going to be a strong oxidizing agent. So I haven't learned about the mechanisms for these yet, and you probably will not learn about the mechanisms for these oxidation reactions as well. But when we do oxidation, is that the gain or loss of bonds to electronegative atoms like oxygen? Is that the gain or loss of bonds to gain of bonds to electronegative atoms like oxygen, right? So I'm gonna draw out the hydrogens here just to make it more clear, right? And also, is oxidation the gain or loss of bonds to hydrogens? Loss, yes. So if I use a weak oxidizing agent on a primary alcohol, that is going to give me an aldehyde, where the carbonyl carbon of the aldehyde, that blue dot carbon right here that I color coded, is that carbon there attached to the alcohol, right? Where look at the original reactant right here. That blue carbon had 1 bond to oxygen, but now when we oxidized it, it gained another bond to oxygen. This double bond counts as 2 bonds, right? And we had to exchange that with a bond with hydrogen, right? Because before, this blue carbon had 2 bonds to hydrogen, but now it only has 1 bond to hydrogen. So we exchanged 1 hydrogen bond for a bond, an extra bond to oxygen. Yeah. Any questions on that? Mhm. Yeah, that's good. That's good. But this is not the most oxidized form because you see how there's one more hydrogen here. We could oxidize it further, right? We only stop at the aldehyde if we use a weak oxidizing agent, PCC. But let's say we used a strong oxidizing agent, Jones. We're going to oxidize the primary alcohol all the way to this carboxylic acid, right? Because now let's look at the blue color-coded carbon here. How many bonds of oxygen are there to oxygen? Double bond counts as 2 bonds. So how many bonds of oxygen are there to this blue carbon? So yeah, three bonds to oxygen, right? 1, 2, 3. How many bonds to hydrogen? How many bonds to hydrogen? 0. Yes. So you notice how here the primary alcohol had 2 hydrogens, but we got rid of those 2 hydrogens to gain 2 more bonds to oxygen. So whenever we do oxidation, we lose hydrogens and we gain bonds to oxygen. Yeah, strong is better. strong is gonna oxidize the alcohol more, right? Well, don't think of it in terms of better or worse, because in synthesis problems, yeah, so that's a good question. Why use weak oxidizing reagents? Sometimes we don't want to go all the way to the carboxylic acids, right? Sometimes we want to get to the aldehyde and then react the aldehyde with something else, like a Grignard reagent. And then you're going to see why when you learn about synthesis problems, right? Synthesis problems is basically that they give you a reactant and they give you the product molecule. But the problem is going to ask you what reactions transforms the reactant to the product. And then some synthesis problems want you to stop at the aldehyde and not go all the way to the carboxylic acid. And then if you want to do that, then you have to use PCC, can't use Jones, right? So don't think of like PCC or Jones is better. Think of it like in terms of what you want to get in the product, right? If you want to get the aldehyde, you use PCC. If you want to get the carboxylic acid, you use Jones. Yeah, because sometimes you want to use aldehyde over carboxylic acid. Right. Okay, so the primary alcohol is the hardest one, the hardest row, right? Because if we use a secondary alcohol, it will not matter what oxidizing agent you use, you're going to get the same exact product, right? Because let's look at the secondary alcohol. How many hydrogens are on that blue carbon? Only one H. So how many times can you replace the H with the oxygen? One time, right? And when we do that, we're going to get a ketone, right? Which is going to be both for PCC and Jones. So if you have a secondary alcohol and you use PCC or Jones, you get the same exact thing, a ketone. Right. How many hydrogens does this tertiary alcohol have here? 0. Can it gain any bonds to oxygen? Can it exchange a hydrogen to an oxygen? No. Right. So it's going to be no reaction, NR. Right. So this is oxidation. And there is one sneaky reaction that you might see here. There is a way for us to oxidize an aldehyde to a carboxylic acid. And which oxidizing agent do you think can do that? PCC or Jones? If you want to convert an aldehyde into the carboxylic acid, what kind of oxidizing agent would we have to use here? PCC or Jones? Jones, yes. We cannot use PCC because PCC's maxed oxidized state is the aldehyde. If we try to use PCC on an aldehyde, no reaction is going to happen. Right? It's just going to stay as an aldehyde. But if we want to oxidize it further into the more oxidized state, carboxylic acid, then we have to use the strong oxidizing agent, Jones. Right? So in exams or homework problems, if you see an aldehyde reacting with Jones, then that's going to form a carboxylic acid, right? Because we see that this carbon here had one hydrogen. We got rid of that one hydrogen to gain an extra bond to oxygen right there. Right. So that's oxidation. Let's move on to reduction. Okay, so there's going to be two types of reducing agents, a weak one and a strong one. There's more, but for 118A, you're going to be introduced to these two first. So there's a weak reducing agent and there's a strong reducing agent. And I know Farhat likes to use a lot of names of these reducing agents. So the weak one is going to be sodium borohydride. Sodium boron hydride, so BH4. And a second step, acid workup. For the strong reducing agent is going to be lithium aluminum hydride. Lithium aluminum hydride. And we're going to see why we need a second step of acid workup when I go over the mechanism. But the weak reducing agent is sodium borohydride, and the strong reducing agent is lithium aluminum hydride, right? Whenever you see these reducing agents here, you always think of a hydride ion, right? Hydride ion, which is going to be a hydrogen with a negative charge. And this hydrogen with a negative charge, is this a nucleophile or electrophile? Nucleophile, right? Because if you think about the term reducing agent, it's a reagent that would reduce another molecule, right? So if we want to reduce another molecule, would that molecule gain or lose a bond to hydrogen? If we're reducing a molecule, will it gain or lose a bond to hydrogen? Yes, it would gain a bond to hydrogen, right? And it's going to gain a bond to hydrogen by this hydride ion here, the nucleophile. The nucleophile is going to attack whatever molecule we want to reduce, and that's how that molecule is going to gain that hydrogen bond, right? And this hydride ion comes in the form of NaBH4, sodium borohydride, or LiAlH4, lithium aluminum hydride, right? And I'm just going to show you what sodium borohydride can react with and lithium aluminum hydride, what it can react with for 118A purposes. Sodium borohydride can only react with aldehydes and ketones. It can reduce more things, but for 118A purposes, think of these two. Sodium borohydride can reduce aldehydes and ketones. And strong reducing agent, lithium aluminum hydride, it can reduce aldehydes, ketones, and carboxylic acids. Right. The weak reducing agent, sodium borohydride here, is not strong enough to reduce a carboxylic acid. But the strong reducing agent, lithium aluminum hydride, is strong enough to reduce the carboxylic acid and everything else. Right. So let me give you a table that would make this more clear. So let me give you an aldehyde. Let me give you a ketone. And let me give you a carboxylic acid. And let me give you the weak reducing agent, sodium borohydride with acid workup. And let me give you the strong reducing agent, lithium aluminum hydride. And the second step, acid workup. Okay. Okay. So let's look at the weak reducing agent, sodium borohydride first. Which one of these three molecules can the weak reducing agent reduce? Which one of these molecules can that weak reducing agent reduce? Aldehyde, yes, that's one of it. And there's one more that the weak reducing agent can also reduce. Ketone, yes. So now if we look at the aldehyde carbene-carbon and the ketone carbene-carbon, the aldehyde is going to be reduced to a primary alcohol. The ketone is going to be reduced to a secondary alcohol. And we're going to see why here, right? Because how many bonds to hydrogen does this carbon have here initially? One. How about this one here after we reduced it? Two. So it gained one bond to hydrogen and it lost one bond to oxygen, right? Because before it had two bonds to oxygen, but now it only has one bond to oxygen here, right? So same thing as for this one here. There were 0 bonds to hydrogen on that carbon, but when we reduced it, we have one bond to hydrogen on that carbon now. And we exchanged it with one bond to oxygen, right? And we said earlier that sodium borohydride is not a strong enough reducing agent to reduce a carboxylic acid. So we're going to say no reaction for the carboxylic acid. Now, if we use a stronger reducing agent, lithium aluminum hydride, it could reduce the aldehyde, giving us the same product, primary alcohol, and reduce a ketone, giving us the same product, secondary alcohol, right? But now for the carboxylic acid, when we reduce the carboxylic acid, we're just going to get rid of the carbonyl, get rid of the carbon double bond oxygen to get the final product there, right? Where we're going to get rid of 2 bonds to oxygen to gain 2 bonds to hydrogen, right? Okay. Yeah, so I'm going to show you the mechanism of reduction because that is shown for the aldehyde and ketone. The carboxylic acid one is a little bit trickier one. And I don't know if Farhat went over it, but I'll just go over the one with the aldehyde first and go from there. So this is the aldehyde right here. And let's say we use sodium borohydride as the reducing agent. Sodium is a positive charge spectator ion, so it's not going to do anything in the mechanism. It's just there spectating the mechanism. The boron here has 4 bonds to hydrogen. And boron is in the 3rd column of the periodic table. So that means that it's one of those weird atoms that when it has 4 bonds, 1, 2, 3, 4, it's not neutral. It will be negatively charged, right? And because it is negatively charged, all of these hydrogens here attached to the boron wants to leave the boron to become neutral. The boron wants to kick out one of the hydrogens. So that's why we get the hydride ion from, right? These hydrogens here are going to be acting as these hydride ions as a nucleophile. And we see we have an electrophile here, the carbonyl carbon, right? Yeah. So, wait, Kathy, are you back? Back. Okay. Okay. So, we left off with this carboxylic acid here, not being able to reduce with sodium borohydride because it's not strong enough. But when we use a strong reducing agent like lithium aluminum hydride to reduce it, we're going to get rid of the carbonyl, carbon double bond oxygen, to get our final answer here. We get our primary alcohol, right? We see that we lost 2 bonds to oxygen in order to gain 2 bonds to hydrogen. Does that make sense? Yes, okay. So now I'm just showing you here the mechanism of a reducing agent reduction reaction. When you see sodium borohydride, you see sodium as a positive charge, and then whatever is attached to it is a negative charge, which is boron. And boron here has a negative charge, even though it has 4 bonds, because it's on the 3rd column of the periodic table, right? So it's one of those weird atoms that is going to be negatively charged with 4 bonds, right? Because you know how most atoms with 4 bonds are neutral, like carbon, oxygen, nitrogen, right? 3 to 4. Wait, what do you mean 3 to 4? 3 to 4. Negative charge. Because 3 to 4. Oh, 3 minus 4. 3 minus 4. Yes, yes. 3 minus 4. Boron is on the 3rd column, so it wants 3 electrons to itself. So when we calculate the formal charge, we're gonna have 3 minus how many electrons the boron has to itself, which is 1, 2, 3, 4. 3 minus 4 is -1, which is why that boron has a formal charge of -1. And because that boron has a formal charge of -1, all of these hydrogens here want to leave with this bond it's attached to, right? So all of these hydrogens here are going to act as a hydride ion, a hydrogen with a negative charge. And would that make it nucleophilic or electrophilic if all of these hydrogens are negatively charged? Nucleophilic, right? So we have a carbonyl here. Is this carbonyl carbon nucleophilic or electrophilic? Electrophilic, right? So in organic chemistry, what attacks what? Does nucleophile attack electrophile or does electrophile attack nucleophile? Yeah, nucleophile attacks electrophile. So one of these hydrogens here of the reducing agent is going to attack this carbonyl carbon, right? But it's going to move with the 2 electrons that it's bonded to with the boron. So the bond and the hydrogen is going to move as we attack. So let's say we use that one. Those 2 electrons with the hydrogen are going to move to attack that carbon right there. So this is the process of reduction here, right? Because let's think about the terms of reduction. Is it a gain or loss to hydrogens for reduction? So reduction is going to be the gain of bonds to hydrogen, right? Because if we go back to the table here, reduction is a gain of bonds to hydrogen, right? What about electrons? Is it the gain or loss of electrons, reduction? Yeah, so reduction is also the gain of electrons, right? Not loss of electrons. Yeah, it's easy to mix these things up, like oxidation, reduction. Yeah, yeah, don't think of oxidation. We're not talking about oxidation here. We're going to talk about reduction. Yeah. So reduction is the gain of electrons and gain of bonds to hydrogen, right? And in the mechanism here, we see that clearly. If we're reducing this aldehyde, we're making this carbonyl carbon gain a hydrogen atom and gain these 2 electrons, which is reduction, right? These 2 electrons and that hydrogen is going to go to that carbon, reducing that molecule. right? Because that molecule is gaining a bond to hydrogen and gaining 2 electrons. Does that make sense? Yes. And what about in terms of bonds to electronegative atoms? Is reduction the gain or loss of bonds to electronegative atom? Loss of bonds to electronegative atom, right? So this is our electronegative atom right here. And the loss of bond is going to be represented by this arrow here, right? And the reason why we have to do this arrow is because when we're trying to make a new bond between this carbon and hydrogen, we're going to break the octet rule, right? This carbon is going to have 1, 2, 3, 4, 5 bonds. To conserve the octet rule, we have to pop one of the bonds of the double bond onto the oxygen, which is showing that loss of bond to electronegative atom right there, which is reduction as well. Right? So reduction, we're gaining a bond to hydrogen, an electron, and we're losing a bond to electronegative atom right there, oxygen. Does that make sense? Like all those arrows here shows that all the different definition of reduction, gain of bonds to hydrogen and electrons, and loss of bonds to electronegative atom, oxygen right there, right? Like, oh my God, when I just explained that right there, like that was a different way for me to view it because I never saw it like this before. I just like memorized like the definitions of oxidation and reduction and what it loses, what it gains in terms of electrons, hydrogens, and bond selection negative atoms. But when I just drew this out right here, it makes more sense now. It just hit me like the more big picture. So yeah, that's good. That's good. All right, that's good. So now the intermediate here is gonna be like this. O minus, and this is the new bond to hydrogen, right? Where if I circled the bond and hydrogen green, that's going to be that green right there. And this is going to be the blue dot right here. The blue dot is no longer double bonded to oxygen. It's now single bonded to O minus. And this hydrogen here was always there, attached to the blue carbon. Now I'm going to just redraw this like this so that it's not messy, right? I'm just flipping the O minus down here and leaving these 2 hydrogens as implied, invisible. Okay, that's the end of the first step. Let's bring in the second step now, H2O plus. What would this do? H2O plus. Yep, O minus grabs the H, kicks out that water conjugate base to give us our final answer, primary alcohol here, right? So that's the reduction of aldehyde. You could do the same thing as reduction for ketone. It's the same exact mechanism, right? To get your final answer, right? Secondary alcohol. Yeah. Carboxylic acid mechanism is not that like straightforward. There's some weird simultaneous steps going on, but I don't think you need to worry about that. For Farhat, I have to check, but for Wei, she didn't go over that, so we won't worry about that. Okay, now let's bring this together with Grignard reagents, which we learned from last office hours, and oxidation reduction here, right? So let's do number. Yeah. So you want this go over 3, 4. We did that 5. Okay, yeah. Let's do 6 here. So 6 here is asking for which of the following reactions would produce the alcohol shown. So they show you the product, and then the answer choices here is the reaction. Which one of these reactions would produce this product? Right. So to make it look easier, I'm going to copy and paste that product and paste it to all of the answer choices here. And I want you to choose the correct reaction that would produce this product. Nostalgia. Yeah, my iPad is like so worn out right now because the screen, I need to replace it. I use Paperlike and I got it since 2020, so it's almost been like 5 years, like 4 years or something. And the pencil I have right now is like being broken down. This is my second pencil. Draw out C. Yeah, let me draw out C. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3, 4. This is 6. C. C is the answer. That is correct. Because when we reduce this ketone with NaBH4, that ketone is going to become a secondary alcohol here, right? Because we're losing a bond to oxygen to gain a bond to hydrogen right there. That's right. You got it. Okay. Now, let me see here. Okay, let's do 8. What do you think 8 is going to be here? Well, first, let me ask you this question. Yeah, it's E, right? None of the above. Because what kind of reaction are we doing here? Acid base, oxidation, reduction, nucleophile, electrophile, SN2, SN1, reduction, right? We're reducing this carbonyl ketone into the alcohol, right? Because we see the loss of bond to oxygen and the gain of bond to hydrogen. So if we do reduction, we have to use some kind of reducing agent, either sodium borohydride or lithium aluminum hydride. None of those reagents are here in answer choices. There's no sodium borohydride, there's no lithium aluminum hydride, giving us none of the above. Right. This is a strong acid, which is not going to do reduction. This is oxidation because we see chromium and a lot of oxygen. So think of that as Jones. That's oxidation. But we don't want to do oxidation. We want to do reduction. Oxygen, that's going to do some combustion reaction. We don't want to do combustion reaction. This is a base, hydroxide ion. We don't want to do acid-base reaction. We want to do reduction reaction. So we need a reducing agent, which is not here. Right. So the answer is E. Okay. Let's do. Okay, let's do this one. This is gonna bring everything you've done in the quarter like reactions kind of together, right? Try this one out. I'm gonna draw out the reactant for you so it's easier. 1, 2, 3, 4, 2, 3, 4, attached to chlorine like that. Okay. And I want you to also label each reaction for each step. Yeah. And let's see. I'll have Elysia walk us through if you're down for that, Elysia. Like explain to how we would do this problem.
Yeah. Okay.
Yeah.
I am a bit confused. I think okay, so is the OH minus or the H2O are those like the either or like options that we can choose from?
Yes. OH minus or H2O, but in this case, we are going to choose the stronger, more reactive one. And which one do you think
Okay.
that would be?
Right. I think that's the minus
Yes, this -1.
because
The water
H2O is
here.
neutral.
Yeah, neutral. This is the
Okay.
product solvent. Right. So OH minus here is going to be our nucleophile here or base. Right. And what kind of substrate do we have here in the reactant?
If we're gonna look at, are we just looking at the carbon that's attached to the chlorine?
Yes, yes.
Okay, that would be a primary
Yes, primary. And chlorine, you looked at chlorine because that is the good.
leaving group.
Yes, right. Now, given these three information, good leaving group present, primary substrate, and whatever OH minus is, which is a strong base, strong nucleophile.
The SN2?
SN2, yes.
Yeah.
Strong base, strong nucleophile on its primary alcohol is SN2. Did you like get that out of your head, or did you look at the chart, the SN2, SN1, E1, E2 chart?
I got that from my head.
Oh, that's good. That's good.
Yeah, I think SN2 and SN1 I'm pretty
Confident
strong.
in?
Yeah,
Yeah, that's good. So what would be the mechanism of SN2 here? Like what's gonna happen?
backside attack.
Yep. O minus attacks this electrophile, backside attack, kick out the leaving group, substituting that chlorine with the OH. And what did we just form here as a result? What kind of alcohol?
That's a A primary alcohol, right?
Yes, primary alcohol. Now that is the product of the first reaction. Let's bring in the second reaction, PCC. What would PCC do to this primary alcohol?
I think what we said from last time was it was a weak nucleophile.
Weak oxidizing agent.
Or
Yes.
yeah, weak
Uh-huh.
oxidizing agent. So if it's primary, it's only gonna form an aldehyde.
Yes. And you could draw out the aldehyde like this, which is the same orientation as the oxygen. But I don't like looking like an aldehyde like that. So I'm going to draw it like this, if that makes sense. Like I'm just flipping the carbonyl and hydrogen around
Mhm.
to show this aldehyde in this form. So both cases would work. Um, so now that's the product of the second reaction. Let's bring in our third reaction now, which is this molecule. When you see lithium, think of that as MgBr. Right. So when you see lithium here, think of that as MgBr, a like organometallic reagent. Right.
Right. Like the Grignard reactant.
Grignard reagent. Right. Grignard reagent.
Grignard. Yeah.
And what charge would this carbon here have directly attached to the organometallic? The
Is
lithium.
that a partial negative?
Yep, partial negative. So that's our star, our nucleophile.
Yeah.
And this is our partial positive. So what will attack what?
It the negative will go the negative will go to the positive.
Right? Nucleophile will attack the electrophile, negative go to the positive, right?
Mhm.
And there's one more arrow that happens here.
Yeah, then the double bond will go to the oxygen, giving it
Mhm.
an extra pair of electrons.
Yep, an extra pair of electrons. And what charge on the oxygen as it gains that extra pair of electrons?
A negative.
Yep, a negative charge. That's right. And what happens to this lithium?
It it leaves.
Yep, it leaves. It dissolves. It leaves.
Yeah,
Goes bye-bye. Goes away.
yeah.
Right. Now, there's multiple ways to connect this, but the way that I do it is I like to star my nucleophile and dot the electrophile. So this represents our neo bond between them to prevent adding an extra carbon or losing extra carbon. You're gonna see that a lot of people are gonna struggle with like connecting these together when they first learn these reactions, like Grignard reagents and connecting them, because they're gonna accidentally add a carbon, lose a carbon, or if they have the right amount of carbons, they're gonna put the wrong groups on them. But to keep track of everything, you could do the star and dot technique here.
Mm.
Now, what is attached to the dot carbon now from this product?
Um, the one that we drew arrows to, like
Uh-huh.
so it with the carboxylic or like yeah the O.
Uh-huh. But
O
no longer a double bond. It's now a single bond because we push one of the bonds to the
right,
O, make a negative charge. Right.
and we have an H there right too.
Yep. You could draw it out or you could leave us invisible, but I'm gonna draw it out for here
Yeah.
so it can make more sense. An H, and there's one more thing.
Um, is it the yeah that
Yeah, that propyl R group, right? Which is 3 carbons, 1, 2, 3, attached to the dot carbon. So we're
yeah.
gonna put that 1, 2, 3 propyl group like this, right? 1, 2, 3, right?
Okay. Is there another way that we could write or connect that propyl group, or it should
Mhm.
be only one way?
Yeah, there's multiple ways. You could, let's say, if you put the O minus right here, you could put the propyl group up like that if you wanted to.
Okay.
Uh-huh. The hydrogen is also here, but I just left it as invisible. Or you could also do it like this if you want. Let's say we put a hydrogen here, O minus here, like that. Right. But this is a more of an iffy way because if you erase the hydrogen, then this looks like one really long bond. Right. Oh, wait, actually, no, because this is a carbon here because it's coming off, it's making a bond to the oxygen. So this is another way you could draw, but it's really weird. So
Yeah.
yeah, that's basically the same thing as this, right? So you could either draw it like this or like this, right? Okay. Now,
Okay.
let's bring in the fourth step, H2O plus. What would that do to this product of step 3?
It deprotonates. So
Yeah.
the
So
um
Mhm.
is it the negative would want to be satisfied, or like it doesn't want the negative, so there's
Yeah.
a hydrogen that
Mhm.
uh it it grabs the hydrogen.
It grabs the hydrogen, and the bond between the hydrogen being grabbed and that oxygen, what happens to this bond here as that hydrogen is being grabbed?
Um, doesn't it become H2O?
Yeah, it becomes H2O because those two electrons are gonna kick off that H2O right there, right?
Yeah,
Those two electrons are gonna go onto the oxygen, creating H2O.
right. And then it'll be an alcohol.
Yep. And I'm gonna leave the hydrogen as invisible to give us this final product here, right? And what answer choice would that be? A, B, C, D, or E?
That looks like A.
Yep. So the answer here is A. Got it. So this was a multi-step predictive product problem where the first reaction we did was an SN2 reaction. The second reaction we did was an oxidation reaction. The third reaction we did was an organometallic reaction or Grignard reagent reaction. And then the last step we did was acid-base reaction. Right. And when you say like what happens to this molecule here, we say that it gets protonated, right? Not deprotonated, because it's gaining a proton.
Yeah,
A proton is a hydrogen. But you can say that this one here is getting deprotonated. That H2O plus is getting deprotonated to water because it lost a proton.
right.
Right. Yes. Okay. Did that make sense?
Yeah,
That's good.
thank
Uh,
you.
no problem. Did you have any other questions you wanted to go over today, Elisa, or was today good for you?
Sorry?
Did you have
I
any
think it
other
cut off.
questions or problems you wanted to go over for tonight?
I did, but I know it's like 10 o'clock, so I don't know.
Yeah, we could go over one problem.
Okay, yeah. Um I'll send one right
Yeah.
now.
Yeah.
I sent it through Discord.
Let me see.
It was either I left two, either one or two. Is a question two or question three.
Question
Probably.
two. Okay. Oh, SOCO2. Also, PCC, we went over that reaction already. I'm gonna go over SOCO2 with you, and then in the next office hours we can finish off the other ones. When does this due? When is this homework due?
Um, Not for a while. I think it's like a next week.
Next week? Okay,
Yeah,
okay.
but I saw like we're kind of on the similar topic.
Yeah, it's good.
Or at least not for SOCl2. I think that's different.
Yeah, it's a different kind of reaction, but it's still on alcohols, right?
Mhm.
Because all of these are alcohol right now, like oxidation reduction, Grignard reagents. This is another type of alcohol reaction here. So this is going to be SN2 like reactions substituting an alcohol. How do I want to do this? Yeah, to a halogen, right? Where the halogen could be chlorine, bromine, or iodine. So let's say we have this alcohol, and we want to substitute that with chlorine, bromine, or iodine. So for chlorine, you could use SOCO2 or PCl5 to substitute this alcohol with the chlorine. But because it is SN2-like, what happens to the stereochemistry, do you think, if it's SN2-like?
Um, I'm I'm not really sure.
Yeah, so for SN2, what is the mechanism? It does what kind of attack? For the
Backside.
mechanism? Backside attack, right? So when we do a backside attack, the stereochemistry here is it going to stay the same as a dash? Is it going
No,
to invert to a
invert.
wedge? Invert, right? So the dash here is going to invert into a wedge like that, right? And if we wanted to convert it into bromine, the reagent we're going to use is PBr3. PBr3, which is going to convert the alcohol into a bromine, but it's also going to invert the stereochemistry of the alcohol. In this case, we have a dash, so we're going to invert that to a wedge, right? But if this starting material here was a wedge, we would invert that to a dash. And if we wanted to do with iodine, I think it would be I2. I forgot what the iodine reagent is. It's not as common, but it might be like PI5 or like I2 something something something. But one of these weird reagents would oxidize the alcohol. I mean, not oxidize, substitute the alcohol with an iodine and invert the stereochemistry like that.
Okay.
Right. So that's that reaction. The mechanism, I don't know if she went over it, but this is how you would predict a product. If you see one of these weird reagents with a halogen, like chlorine, bromine, iodine, just substitute the alcohol with the halogen that you're given and invert the stereochemistry that you're given.
So it's similar, but in this case, like when we have like 2 of something or 3 of something or 5 of something, we have one of them substituted or like backside attack and substitute for that halogen or like that
Right.
chloromine. Or,
Yeah, that's correct. That's correct.
okay.
You got it. Yeah. So if we look at this right here, how would what would be the major products? What letter would be the major product?
Well, we know it's going to be any of the ones. Oh, okay. I think it's F.
F. Yep, you got it. That's it. That's the major product.
It's stereochemistry, and we have chlorine.
Yep, the stereochemistry flipped from a wedge to a dash, and we substitute the alcohol with the chlorine.
What does T mean?
Oh, T is triethylamine, which looks something like this, where there's 3 ethyls on the amine right there, and this is what we call an A product solvent. And that A product solvent is just going to facilitate the reaction, stabilizing the intermediate, but it's not going to do anything in the mechanism, right? It's just there watching.
Okay.
A product solvent. It's like THF, DMSO, like those A product solvents for SN2. It's just there.
Okay. Do you think this is like a common one that we would be given, like for an example on the exam, or are like
Yeah.
our main ones the DMSO and stuff?
This is a common one for anything with chlorine. Like when you see any reagent with chlorine and you use a product solvent, T or pyridine is a common one for that. So
Okay.
just note that T is an A product solvent. You could also see pyridine as a product solvent as well.
Okay. That makes sense.
Yep.
Thank you so much, Brian.
Yeah, no problem, Alicia. Yeah. Have a nice night and enjoy your Thanksgiving break.
Thank you. Happy Turkey Day.
Happy Turkey Day.